All right, welcome everybody to lesson 2, and this is also coinciding with chapter 2 in second. And now we're going to get into some of the application side of statistics stemming from our introduction. And today what we're going to get into is we're going to begin the first layer of our scaffolding of knowledge, and that's understanding what we call measures of central tendency. And this extends from the descriptive statistics side of things, where we try to make sense of the numbers. So the learning goals are set here on this slide. You can take a look at them. I've broken this section up into two parts. The first part will be understanding what measures of central tendency are, the definitions, when do we use them. And the second part of chapter 2, it's a little bit odd, and it's actually getting into what we call measures or levels, scales or levels of measurement. And we need to begin to describe some of these measures that we use. Some measures that we use are very precise, and some measures are not so precise. And we'll spend some time unpacking those. I'm also going to give you a chance to do some practice work calculating measures of central tendency, both by hand and also using SPSS. There'll be some practice data sets that you can access, and I'll give you some instructions in terms of how to do that. And that will be a nice preamble before we get our first assignment coming up, where we begin to combine aspects related to Chapter 2 and Chapter 3. Okay, so before we get into Chapter 2, let's recap from our Lesson 1 and to kind of bring us up to speed here. So we start with research, we start by taking a sample from a population, because the sample is supposed to represent the population, and it's really hard to measure the population, and so we infer from the sample to the population. It's much more workable, it's much more measurable, right? So from the sample, we take a series of measures, we do these things that are important to us or to the researcher, right? And then we have to decide how we organize the information, like this numerical data, to help us understand the sample. Right, that's what we want to do. And so this is where we begin with descriptive statistics to describe the sample. And I can't emphasize more how important describing the sample is. Descriptive statistics are probably some of the, I would say, the more entry level or basic side of statistics. But in terms of critical thinking, at the very least, it's this aspect of description or characterizing the sample is really, really important. Why is that important? Because we take from the sample and we project onto, or we infer onto, the population. Knowing something about the sample allows us to know something about the population from whence the sample came. So we're going to begin by describing what are called measures of central tendency. And titles like that, I remember back in my biology days, I would get these brand new terms I had to deal with, and it got a bit overwhelming for me. It was one more thing to memorize, one more thing to know, until I finally got smart and began to kind of break the titles down. And so a measure of central tendency, even the title, tells me something, right? So what I know is we're taking a measure of some kind, okay, whatever that's going to be. We know that part. The second part of it, the second part of it is there's going to be something that is central to it. So when I think of the term central, what does that mean to me? Well, I think of center, or I think of middle. Okay, so I'm looking at some kind of middle measure of something. But then you've got this last term here, which is tendency. And so what does tendency mean? Well, tendency can mean a drift towards something. So if you want to, rewrite the term measures of central tendency, which is the more appropriate term, really what we're getting at is we're getting at some form of measure that drifts towards the center of all the measures. That's what we're talking about. Another way to describe that might be a single score that actually represents all the scores. Now we know that a single score is not going to represent everybody. We know that when we have midterm scores, right? You know, and the professor says, well, the class average was 70%, and you look at your paper and you got, 82, well, you're above average. Someone else might have looked at one and got 55%. Okay, I'm below the average. Rarely does the entire class get 68%, right? That'd be a big problem, actually. I think if I was a professor and the class average was 68% and every student got 68%, that would just be very, very bizarre. So there's going to be more to this that we're going to add in Chapter 3. We're going to add a little bit to this single score, but we have to start somewhere. And so how can we calculate this one score then? That becomes the question. And is there more than one way to do that? Let's take a look at those. So there are 3 ways to go about gathering our measures of central tendency. And researchers are not limited to simply using one. You could use all 3 if you wanted to, depending upon how the data is presented. But very often there's going to be choices to be made, right? And so there's 3 different types. The first one is called the mean, or what you and I might know it is as the average. Okay, the average. And we're going to get into them. I'm just warning you ahead of time. The next slide has a bit of math coming up, and so just be aware of that. The second measure of central tendency is the median. And again, this is what we call the midpoint of the scores, right? And so far, both the mean and the median meet our definition of measures of central tendency, this drift towards the middle. The average is the middle, and the median is also the middle. Okay, so that's very good. The third one is what we call the mode. Now, the mode is the most frequent score that occurs in a set of scores. I'm going to give you some examples of this. Rarely do you see the mode in any research journal article. You just don't see it. I think I've seen it once, and I've read thousands of articles. You will see the mean very often. Sometimes you will see the median. So those 2 for sure. The mode has its uses, but probably we see that more in the sense of a frequency. So you don't see it that much. But let's get into taking a look at some of the calculations of these and how do we go about actually deriving these measures of central tendency. We'll start with the mean on the next slide. So I promised you some math, and here it is. And don't be alarmed by this equation. It's actually all it is simply a fraction. Part of the confusing side of it might be all the symbology in the equation, but it's actually not too bad. So let's unpack this. On the left-hand side here, we have a symbol called with an X with a bar over top of it, and that's going to be the mean value or the average of a series of scores in a sample. You'll see the mean in journal articles expressed as an X bar. Sometimes you'll see it as the word mean, sometimes as a capital M. Depends upon how the journal actually does their own nomenclature. I do apologize for it. I know it's a bit confusing, but join the club. On the numerator of the mean, what we have here is you've got the symbol sigma, right? And what sigma means is the sum. I'm summing up a bunch of things. And what am I summing up? Well, I'm summing up all these individual X scores here, right? Now, don't confuse the X with the X bar. They are different. This is an individual score in a set of scores, and I'm going to have a whole bunch of them. If I've got a sample size of 20, for example, I'm going to have 20 different individual X's that I'm going to be adding together to get a total sum, right? So the numerator is simply I'm summing up all the scores in a data set from a sample, and then I'm going to divide them by the sample size. And the sample size is simply the number of individuals in the sample that actually gave some sort of value. So let's say that let's say on the top here, add up all the scores and the total sum came to 20, and I had, say, 5 in the sample. I would divide 5 into 20, and that would give me a value of 4 for my mean. Okay, so I want you to try a couple here. So I've given you 2 sets of values. Let's say that these might be 2 different variables I'm measuring from the same sample. right? So I've got, how many do I have in the sample size? Well, in set 1, I've got 5 in the sample size because I can count them up, 1, 2, 3, 4, 5. Same in set number 2, I've got 5 in my sample size, 1, 2, 3, 4, 5. Perfect. So to calculate the mean, what I do is I sum up all the values in each set, and I simply divide by the number by the number of individuals in that sample. So set number 1 is pretty straightforward. You don't even need to do any calculations with that. We know what the average is, or the mean is, for set 1, because that would be 5 plus 5 plus 5 plus 25 divided by 5. You're going to get a value or a mean of 5. Set number 2, I want you to try, and hopefully you've been doing that with your calculator. If not, you can double check. I'm going to give you the answer. If I add up all the values here, so let's go 10 plus 12 is 22, plus 14 is 36, plus 10 is 46, plus 20 is 66, and I divide that by 5, I should get a value, or a mean value, of the scores of 13.2. Okay, so try that, double check it, and see if you get the same values that I do. Okay, let's take a look at another example here. And we've got a few more data points. They're all a little bit different. And let's calculate the mean, or the average high temperature. And again, this is canned data from, it's probably even fake data, from the years 1993 to 2002. And so these are the daily high temperatures for these values. So 1993, the daily high temperature was 59 degrees. 2002 it was 47. We want to know what the average daily high temperature is for all these years combined. And so to find the mean, we want to find the sum of all the temperature data points first. And so we do that. So we add them all up. We add 59 plus 50 plus 50 plus 13 plus 40, et cetera, and we get a total sum score of 465. And we divide that by the number of temperature measures. In this case, there was 10 measures that were taken. And so the average, or the mean high temperature, is around about 46.5. Let's just stop there. Hang on a second, let's add this little part there. So this would be our conclusion then. The mean for the daily high temperature between the years 1993 to 2002 was 46.5 degrees. I'm assuming that's in Fahrenheit. But note that we use one value to measure all the values, but we know that every single one of these values, the individual values, are actually different from the average, right? So you begin to see some of the fuzziness of the values here, or the fuzziness of the average temperature. It gives us some information, or an average kind of glance at what was happening across all these years. But there's an awful lot of individual variation, or an awful lot of individual variability, maybe with the exception of 1998 and 2002. They were pretty close to the average. But the other ones were far from the average. As a matter of fact, if you take a look here in 1996, we see that the average high temperature was only 13 degrees Fahrenheit. Okay, now that's a little bit odd. You take a look at all the other values, and this one sticks out. Right? I remember the old Sesame Street song on TV when I was growing up, one of these things is not like the other. And so we see this. So let's just stop here for a second and describe what we call these values that are not like the other. We call them outliers. And we need to address them in the context of understanding the means and the averages. We'll do that on the next slide. So this is an extension from the previous slide, and it kind of describes a little bit of what we saw with that 13-degree high temperature. That 13-degree high temperature wasn't really on par with the other values that we saw. Okay, this happens sometimes in data. We get these values that are extreme, one way or the other. Like that 13 could have been 130 degrees, for example, and it would have stood out. And we call these values outliers. And we have to be aware of outliers, because outliers in particular have a very profound leveraging effect on the average score, or the mean score. And I'm going to show you in SPSS how to look for these outliers. There's a way to look for them. It's pretty easy to see if I only have 10 individuals in my sample, but what if I've got 4,000 individuals in my sample? How do I go and I find these outliers? And so one of the problems with outliers is we go, well, is that really the case, or was there an issue, right? I think the next slide we get into a little bit more about what might have been some of the issues as to why this outlier showed up. But the bigger question is, what do we do with them? Right? What do we do with the outliers when we see them? And so this little joke here, this little figure is this, I can't remember what type of, looks like a quadratic function back from my Algebra 11 days. And all the data points on here, let me put on my little pointer here. Where's my little, there we go here. There's my laser pointer. There we go. So all these little data points here are behaving and following the trend line here. Again, this looks like a quadratic equation of some sort here. And then I've got a data point here that is all on its own. And he says, hey, your theory is wrong. And notice what the temptation is for the researcher. He says, outlier, there's a problem with you. But the question is, we don't know if there's a problem with the outlier data point. Maybe that really is the case. And this becomes an issue, but also an issue for the researcher, but also we see it as a limitation for the mean. Extreme scores will leverage or push the mean one way or the other, right? So we need to describe that in the next slide. And again, just to highlight this slide here, here we have, and I've highlighted in yellow, 1996, we have this outlier. And the question is, what to do when outliers appear, right? How do you handle this? Do you simply just go, well, let's let the machine handle it, run the average, run the mean, or are there some things that we can consider? So when we have outliers in data, you have to do something with them, right? What might have been the cause of the outlier? Why is there these one or two data points that are simply sitting way far out of where everybody else is, right? So a lot of times we often think, okay, well, there's these abnormalities with the data. What do you do? Well, what the researcher would do, you don't have to do this if you're not the researcher, but what the researcher would do is you would review the methods that you did in order to gain the numerical information in the first place. So sometimes there's issues with measurement error. A lot of times this happens. I've had it happen to me before back in my master's degree. I had to go back and take a look at the data. Sometimes it's simply just I recorded the value down correctly by hand. But there are sometimes some other issues that can come up, and one of these things might be what we call instrument calibration. Instrument calibration in a lab, like an exercise physiology lab, when we tested the Vancouver Canucks, we eventually, at some point in time, after about 10 or 12 different tests on the same metabolic cart, we had to shut the machine down and then recalibrate it because we found that some of the values would begin to drift upwards. And so instrument calibration is an important thing to look for in a research journal article. Now, instrument calibration takes different forms, right? It can take forms related to surveys. Surveys are often calibrated by virtue of their reliability and validity. We get into that in chapter 6 coming up. But if I gave a survey to someone, sometimes the error may not be necessarily with the survey itself, but it may be with the participant. Did they follow all the directions associated with a particular survey? Did the researcher give them the appropriate directions and instructions? So there's some small things along the way in terms of communication or in terms of how a person understands the question. And so if you got things flipped around here as an example, let's say that you gave somebody a survey and you asked them to rank something on a scale from 1 to 5, where 1 was excellent and 5 was very poor, but the respondent got them backwards. They think 5 is excellent, and so they responded backwards. That can also happen, right? And sometimes it actually might be the real deal. Your outlier really is as the world is. And so you've got to do a little bit of sleuthing to get around that. Now, you still may go through all these procedures of looking through your methodology and you still have an outlier. And there still is the question, do we include the outlier in the data? And that's a really tough question for the researcher to answer. You can't just simply cherry pick your information because it's going to fit your theory. And that was the whole point of that cartoon on the previous slide. There might be some indications where, yes, this outlier needs to be removed, but there's got to be some justification for it. And usually it's a collective decision with the research team and not the individual researcher, her or himself. So the second measure of central tendency is the median. And it's a bit of a weird definition. It's the point or the score at which 50% of the remaining scores, now that's the number of scores in the sample, okay? That's what I mean by that. 50% of the remaining scores fall above that value, and 50% of the scores fall below it. That's what the median is. It works really well if you've got an odd number in your sample. It gets a little bit of an adjustment if you have an even number in your sample. But the next slide will explain this a little bit better. So because outliers can affect the mean, sometimes the median might be a better measure of your central tendency. Or what you can do is do both. I've often done both. Sometimes I'm just not limiting myself to a mean. I often will kind of do a bit of a double check and see what the median is, and then see how close both the mean and the median are together. So here we go. Here's a series of scores. I'm not sure what this value is from here. So anywhere from the lowest score of 5 all the way up to a score of 59. And I do believe it's an odd number of scores. That's right. So there's 11 scores in there. Where's my little highlighted pen here and my laser pointer, right? There's 11 scores in there. And so to find the median value, what I do is I take the total number of 11 and I find 50% of the values that fall below that central value and 50% of the values that fall above it. So I've got, if there's 11 scores, I've got 10 scores left over. That means 5 scores fall below it and 5 scores fall above the central one. And so my median in this case is going to be 49. That's what the median is going to be. And again, it works really well if you have an odd number of scores. You have to do a little bit of an adjustment if you have an even number of scores. So for example, what if I had 10 values, right? Instead of 11, I've got 10. How would I calculate the median then? We're going to talk about that. So let's go back to our example of our average, or our mean high temperature for the years 1993 to 2002. And in this case here, what we have is we've got 10 scores and we want to find the median. But the problem is, if I look at 50% of the scores that fall above and 50% of the scores that fall below, I end up with 2 scores in the center here. Right, so I have my 2 scores, 49 and 50. I've got 4 scores that fall above it and 4 scores that fall below it. And so all I would do to get the median score is I would actually take the average of the 2 individual scores. So I would take 49 plus 50, that equals 99, divide that by 2, right, to take the average. And so my median there would be 49.5. So you can calculate the median whether or not you have an odd number of scores. That's the easier way to do it. Or even if you have an even number of scores, I can simply take the average of the two middle point scores here. So just a couple of things to remember before we move on. We're going to actually take a little bit of a deviation from our course and talk about percentiles on the next slide before we get into the final value of the mode. But before we get there, let's just remember that the mean is the average of the set of values, while the median is the middle point in a set of cases or a set of scores. And because the median cares about the number of cases, right? Trying to find that middle point, 50% of the scores fall above and 50% of the scores fall below, the outliers do not impact it. That's why you can use the median if you have outliers in your score. And the median in that case is going to give you a better representation of what the average score of that set of scores is. Better than the mean. Remember, the mean can be leveraged up or down depending upon the extreme value of the outlier, whether it's too high or whether it's too low. The median will give us a sense of what the middle is, at least a better sense of what the middle is based upon the scores. What I find really fascinating is when I do my research, I will look at both the average, both the mean and the median. And I think I might have mentioned this before. I'm actually always quite surprised as to how close they are together. So I kind of do that as a little bit of a validation. I usually gravitate towards the mean, which is what I use mostly. But as well, I'll also take a look at the median, just as a bit of a backup, right? You always want to have some redundancies placed into how we analyze data. And so I'll take a look at both. I rarely look at the mode though. But before we get into the mode, I want to just describe a little bit about percentiles, because percentiles come up a little bit later on when we get into what are called z-scores. That's a little ways down the road, but I want to chat with you about them first. So let's pause here for a bit, and I want to talk a little bit about percentiles, because in some ways we've kind of talked about them with the median. And you're going to see percentiles in the literature from time to time, and they're a good little descriptive. Right. So percentile ranks are used to define the percentage of cases equal to and below a certain point on the distribution of scores. We saw that already with the median. The median is a certain point in a group of scores where 50% of the scores fall above and 50% fall below. So the median is always going to be the 50th percentile. That's how we want to describe that. Let's say, for example, we have different percentiles though. So let's take a look at a score that scores in the 70th percentile in a series of scores. So what that means is that the score received is at or above 75% of all the other scores in the distribution. That's what that means. So if someone came to you and said, or if I gave you your midterm back and I said to you, here's your midterm score, but I'm giving it to you in percentiles, and I told you you scored in the 92nd percentile, you'd be pretty happy with that, because that means only 8% of the class scored better than you. You were in the top 10% of the class in terms of your midterm grade. Now, the thing is, if I came to you and I said, well, here's your midterm, you scored in the 14th percentile, you might not be so happy, because that means that the score received is at or above only 14% of all the other scores in the distribution, which means that you're in the lower 15% of the class, and that's not so good. So percentiles give us a sense of ranking within a certain series or a certain case of scores. So our last measure of central tendency is the mode. And the mode is the most frequently occurring score that you're going to see. It's also the least precise measure of central tendency. And I can tell you right now, you are rarely going to see the mode in the literature that you read. Journal articles that you read, you will rarely see the mode. I think I've seen it once, maybe twice. That's about it. And it's simple. The steps to calculate the mode are very easy. You list all the values that you have in the distribution or your set of scores, and you tally the number of times each value occurs. So if I had a set of 10 different scores and I saw the value number 3 occurred 5 times out of those 10 scores, the mode would be the number 3. So the mode is simply the value that occurs the most times that you see in a set of scores. It's the one that actually departs. I said before that the median and the mean sometimes are fairly close together in terms of their values. The mode is a little bit finicky. Sometimes it's close and sometimes it can be quite far away. I rarely look at the mode unless I have to. So here we have 2 examples on this slide. So here we have, it's a party affiliation. We've got Democrats. There's 90 people said they were Democrats. Republicans, 70 people said they were Republicans. And independents, 140 said, no, I'm an independent. So what would be the mode in this case? Now this one's a little bit weird, because we want to say the most frequently occurring number is 140. That would be the mode, but it's not. In this case, the mode would be independence. That would actually be the mode. Sometimes this happens when you associate values and names to numbers. If you're trying to sort out what the mode is, the most frequently occurring score is actually going to be independence, not 140. 140 is simply the number of independents. but this is the most frequent number here. Most people said they were independent, so that then becomes the mode. Another example is down here at the bottom, and so we have, here's my laser pointer here. If I gave you a series of numbers, right, 1, 2, 3, 4, 5, all these values here, and I asked you what the mode was, you would take a look at the greatest occurring frequency. Well, the value 3 occurs 3 times, and so that would be the mode. The value would be 3, right? Couldn't be 1, couldn't be 2, definitely can't be 5 or 6. So it's the most frequently occurring value that becomes the mode. I mean, you might be thinking to yourself, well, this is getting a little bit complicated. How would I ever do this by hand? Well, the wonderful part about using an SPSS package is that you don't have to. I could give you a set of values, 4,000 pieces of information I were to ask you on a particular variable or attribute, calculate for me the mean, the median, and the mode. And SPSS can do it for you in a half second. It's a very, very rapid output. And so this is kind of the long division way of looking at things, just to kind of explain the concept. But in actuality, we use SPSS, and there's other programs too. There's R and SAS and those programs. We would use SPSS to do that. Okay, but again, this is the mode. So before we get into the different types of measures coming up, that's the second part of this presentation. I want you to do a little bit of practice, just with some hand practice here. Bring out your calculator if you want, or you can do it by pen and paper. That's fine too. And I want you to calculate the mean, the median, and the mode for the set of scores that I've given you. Okay, that's what I want you to do. So find the mean, the median, and the mode for the set of scores that I've given you here. And I'm going to pretend that you've paused the slide and you've done this. And so I'm going to give you the values, at least the scores that I have, and let's see if you line up with mine. So I calculated the mean of the set of scores to be around about 7.5. For the median, I had 6.5 as my value. You can see that the mean and the median are close together. I'm not sure if one is a big difference between the two, but again, these are estimates of the trends toward numbers. These are the middle values, right, of the set of scores. Now the mode's a little bit interesting. Remember what the definition of the mode is. The mode is the most frequently occurring score. So in this case here, we actually had 3 modes. This would be a trimodal part of the data set. And it's 4, 5, and 12. And we say 4, 5, and 12 because we see, where's my laser pointer here, we see that we had 2 values of 4, 2 values of 5, and 2 values of 12. They had the highest number of the occurrence of scores compared to all the other values that occurred only once. And so you can have situations where the mode can be more than one value. It can be bimodal. You might have two scores that are most frequently occurring. In this case here, we have a trimodal set of values where we have 4, 5, and 12 are the mode. Now, it's really hard to interpret this score, isn't it? Right? When you think about this, if it's a measure of central tendency, and now I have 3 values, how useful is that to me? Well, in this case here, it's probably not that useful. Sometimes it can be useful. Sometimes bimodal scores, that kind of gives us an idea. But later on, we'll get into something called a bimodal distribution, which is more meaningful. But just be aware that the mode can be more than one score if it's the most frequently occurring value in a set of scores. Okay, we're getting into this second section here, and we call it scales or levels of measurement. And I'm afraid it's going to be, or at least at the first appearance, it's going to be one of these areas where you're going to go, oh, one more thing I have to memorize. And it's true, there are some characteristics and attributes that we do need to know. But it does have applications for what type of statistics we can use later on. And so think of understanding levels of measurement as one more brick in our wall or our scaffolding of understanding of statistics. Now, before we start into measures, this slide actually I'm slipping in after the fact, after I've recorded all this, because what I noted in my script, and you'll notice it coming up, is I will drop in the term variable, and I apologize for not defining that ahead of time. It becomes part of one's nomenclature, and I need to define what that is. I looked through the textbook as well to see where Salkin defines it, and actually the page numbers are incorrect, and so I don't really know where he defines variable. So we need to define it because it is linked in with measures. And so a variable is this. A variable is some sort of characteristic or attribute of interest in a sample, right, that can change. That is to say, it can vary. So vary is the root word of variable. There's some range for this attribute or characteristic to change. It might be low one day, it might be high the other. Mood is a great example of a variable that can change even minute by minute, right? If you're watching a dramatic movie, for example, what's your mood? Oh, you're kind of elevated here, and your mood is a little bit not so elevated 10 minutes into the movie. So it's something that we know can change, and in some cases we expect to change. So here's some examples of variables. It can be a score on a test, right? How did your midterm score vary from the first midterm to the second midterm, right? How did it vary, or how did it change? The variable would be your midterm score, okay? It could be intelligence, right? Good luck measuring that. But if you had a robust measure for intelligence, and you measure someone's intelligence, going into, grade 3 versus when they leave high school, we would expect a change or their intelligence score to vary, assuming you could use the same test. In the physiological realm where I hang out sometimes, we take a look at one's ability to consume oxygen. Right? If someone is very aerobically unfit, they have a low oxygen carrying capacity or low oxygen consumption, put them on a 6-month running program, you measure them again, and lo and behold, their oxygen consumption has increased. It varies, and in the case of oxygen, it varied in a particular direction. It increased, but you're still measuring the same thing. So we apply tools and instruments to measure the change in variables. And so sometimes what happens, and you'll notice in my language coming up, I will say something like a continuous variable or an ordinal variable. Continuous and ordinal, even though they describe the types of measures that we use, sometimes we use them as adjectives to describe variables. It describes how I'm measuring that particular variable. That's how that works. So you'll hear it. If I say, a nominal variable, it describes how I'm measuring that particular variable. If I say something like, ordinal variable, it describes how I'm measuring that particular variable of interest. So here we get into measurement. And again, this is going to be a little bit on the I guess the dry side of things, but nevertheless, it's an important area for us to get anchored into. And so we know that measurement is the assignment of values to outcomes following a set of rules. To be a little bit more specific, we're not going to measure weight using a ruler. We're going to use the instrument that is most appropriate, and we're going to use the units of measurement that are most appropriate. So for weight, I might use newtons or pounds as an example for my unit of measurement there. But in statistics, there are 4 levels of measurement. Each of these have particular characteristics, and there is a scale moving from very precise to less precise. And so in the slides coming up, I'm going to begin with the most precise level of measurement and then move down into the least precise level of measurement. And so sometimes in research, researchers are limited by the instruments that they use in terms of their level of precision, right? And so sometimes we think, well, why couldn't have the researcher done a level of measurement that was more precise than what they used? especially if you know there's other precise measurements available. Well, sometimes that might be due to the type of equipment or finances, right? It costs money to have some of these very precise levels of measurement. And so sometimes researchers use whatever is available to them within the bounds of their research paradigm and their research structure. You can't just simply go and use less precise measures. I mean, those measures have to be valid and reliable. That's coming up in chapter 6. So there are some boundaries put on these things. But what we do get into a little bit later on, and this is highlighted in yellow at the bottom of the slide, is the level of measurement that I use dictates what specific measure of central tendency I can use and other specific statistics, right? So you've got to be aware of two things now. Number one, what level of measurement am I using with my data set, and what statistics will work with that level of measurement? One of the common mistakes with undergraduate students is they will go and use something like a frequency count and apply a t-test to it to look for differences between two groups, as an example. Well, you can't do that, because a frequency measure that you might use, a counting or a percentile or a mode, for example, you can't go and run a t-test with that. You've got to use something else. And so one has to be aware of this. And I've seen mistakes even in journals where the researcher used the incorrect statistic to actually analyze the data. Right? So you've got to marry your statistics with the level of measurement, and that's why these things are important. So we can divide up our scales of measurement. Let's begin simply and put them into two different categories. There's going to be some subcategories of these two major categories here. But we can say that measures can be continuous or they can be discrete. And so a continuous variable is something that has an infinite number of possible values. Infinite, which means if we had the ability to measure to the smallest nth degree, that's what we would use. So an example of this might be any value between, I just picked these two digits, between 5 and 6. So that means that we'd be able to measure down to the, I don't know, what is that, the 20 decimal places, or even further. So 5.1223895, et cetera, et cetera, et cetera. How far can you go? How thin can you slice that salami, as I like to say it? So continuous variables are precise. And the precision is only limited to the type of instruments that we use, right? There's limitations to human ingenuity and human creation with these things. We're not omnipotent, we're not God. Right? Only God knows what the true score is. We try and get as close as possible to it. So continuous values or continuous measures, try and get as close as you can to the real measure. But again, there's going to be some limitations. It's also the most precise. Discrete variables is a variable that can only take on a limited number of values. It could be something as small as, for example, in an examination, pass or fail. Right? That's a 0 or it's a 1. You get your one or the other. There's no in between. Well, you almost passed. No. Discrete variables in that case is you either passed or you failed. Right? You can have ranges though, of course. Like you can have values. Going back to the same digits I used before. Maybe on a scale from 1 to 7, you're going to circle either a 5 or a 6. You can't circle a 5.5 because that's not how the measure is bounded. It's bounded by a single digit. No, you circle the 5 or the 6. Don't circle 5 and 6 because you can't do that. It's one or the other, right? And so we'll talk more about discrete variables and continuous variables coming up. So when we break down the scales of measurement here, we see there's two subcategories under each one. So under continuous, we've got ratio and interval variables or measures. And those are pretty similar. There's only one slight difference between the two. And then discrete variables, we have ordinal and nominal. So I want to break those down for you. Now a continuous measurement that is classified as a ratio measurement is again on this continuum. Like there's an infinite number of possibilities that you could measure it down to if you had the ability to do it. The one thing about a ratio variable or a ratio measurement is that it's characterized by the presence of an absolute zero on the scale. Okay, so age is an example of that. It's really hard to have an age below zero, right? You've got a starting point that is zero, and then once you're born, you begin to move forward in terms of age. And age is a bit of a social construct. It's, it's how many times the Earth goes around the sun. There's all those things associated with it. But we know what years are, right? But we can also break down age in terms of years, months, weeks, days, hours, minutes, seconds, fractions of a second, because your age keeps changing, right, by virtue of tiny, tiny fractions of a second as time rolls forward. So this is why it can be it can be infinitely small, and which is why continuous variables can be so precise. But ratio continuous measures have to have a zero as a starting point. Now, an interval measure, that is also a continuous measure. It's the same thing, right? An interval measure is the same thing, except that the zero on the scale does not mean the absence of the item. So if we measure, for example, temperature in Celsius or in Fahrenheit, for my American friends, you can actually have temperatures that are actually below zero. So it can actually fall below that. Kelvin, if I remember my science correctly, you can't. 0 Kelvin is absolute zero. You can't go below that. But some of the scales that we use, Celsius and Fahrenheit, can have a zero, and you can actually measure things below zero. The coldest I've ever experienced was minus 40 degrees Celsius in Edmonton one Christmas. So it was well below zero, and yet there was still the scale of measurement in between, down to these infinite slices of salami, so to speak. So under the category of discrete measures, we have our first, which is an ordinal measure. And we can often think about ordinal measures as rankings. So, for example, where you finish in a race. Did you finish first, second, third, 48th? Right? You're kind of ranked in terms of how you finish. And you might see this on surveys that you might fill out. You might have a number associated with a certain characteristic or a descriptor. So the example I've given here is strongly disagree, disagree, agree, and maybe those values are 1 is equal to strongly disagree, 2 is disagree, and 3 is agree. Not a great scale, I understand that, but you kind of get the sense of things here. There's an ordered response to a question, or an ordered response to some sort of performance. Now, one of the issues, and this is a limitation of ordinal variables or ordinal measures, is that we don't know how much higher one is from the other. We know that with continuous interval scales, we know that 1 degree Celsius is higher than 2 degrees Celsius, and we know by how much, because that's pretty consistent in between. But with ordinal measures, we don't know. Someone could finish first in a race, the second person might have finished 2 seconds behind them, and the third place finisher was 5 minutes behind. We see that in the Tour de France sometimes. Right, so it looks great on paper. Yeah, you finished third, but you were 5 minutes down on the leader, and the second person was only 2 seconds down on the winner. So we don't know the difference in between the rankings, so to speak. And that even goes with scales like strongly disagree, disagree, agree. We don't know the range in between those scores. So, if strongly disagree in this example here was a 1 and disagree was a 2, just because you circle both doesn't mean you're going to give a ranking of 1.5. That's verboten, that's forbidden, that's not allowed. You have to choose 1. And so when you choose 1, you lose some of its discriminatory power, or another way of saying that is you lose some of its precision. Right? So that's the limitation with ordinal scales. They're not useless. None of this stuff is useless, by the way. Right? You can always find a place to use it, but we have to begin to acknowledge some of the limitations. And our last section under discrete measures is the nominal measure, or you may want to look at it as the name measure. Okay, and so the characteristics of these outcomes fits a one and only one category. So if I were to ask you, what city were you born into? You might say Vancouver or Sydney, right, or Budapest or Hong Kong, and that would be it, right? So it's a bit of a different one. It's a nominal variable. It could be something like a color. What's your favorite color? Well, it's blue. You can't have two favorite, I guess you could have two favorite colors, but what's your favorite color? Well, you're going to give me something. Well, my favorite color is blue. So you begin to see that these categories it's really hard to order these categories meaningfully. As a matter of fact, this is where you might want to use the mode, which is the most frequently occurring city, or what is the most frequently occurring color in this set. You begin to see now how sometimes our measures of central tendency, you might have specific ones that line themselves up really well with levels of measurement. It's also the least precise level of measurement. I mean, it's really hard to take an average of the city that you were born in. Do you catch what I'm throwing? You could take an average of an ordinal measure, like on a scale from 1 to 5. You could take an average. You're not supposed to, but you probably could, because those are numbers. But when you get to nominal measures, it's more challenging, right? It's much more challenging. You take an average of all the colors, you actually get white, believe it or not, because white is when you refract light, white goes into all the different colors of the rainbow. So when you average all those together, you can actually get an average color. But things like cities, or even things like a personal name, how do you take an average of someone's name? Well, you can't. In that case there, you'd actually have to use the mode to determine which is the most frequently occurring name. So just a few things to remember here. Any outcome that one is measuring, and again, you may or may not be doing measurement at some point in time in your academic tenure, but you can look for these things. Any outcome can be assigned to one of 4 scales of measurement, right? These scales of measures have an order. We go from very precise to least precise. The continuous variables, again, are the most precise data. And so that's ideal. If you're measuring something and you could measure something on a continuous scale, that's fantastic. That's the gold standard. And the reason is this: what you can do is, from your continuous data, I can pull out ordinal data, I can pull out nominal data from that, or dichotomous data. So all the precise scales, the continuous variables there, contain all of the quality of scales below it. So continuous data is what you want. The problem is you can't always get continuous data. So to pull things together here, I've titled this slide, When to Use What. So depending upon the type of measurement that I use, when do I use our measures of central tendency? When do those overlap? So here we have it. We want to use the mode when the data are qualitative, either categorical, a category of something like a name, for example, or a city, or nominal. And they only fit into one category. I think I mentioned that in the previous slide. Really, if you're looking at the measure of central tendency for things that are category, you put them into categories, right? Hair color, for example, you'd want to use the mode. We can use the median, and we want to use the median when we suspect that we have extreme scores or outliers in the data. Okay, you can use the median then. We want to use the mean when the data do not include extreme scores, that is, say, no outliers, and are neither qualitative, categorical, or nominal variables. Now, there's some, you might ask, well, what about if it was ordinal? Could I use the mean for an ordinal variable? Remember that an ordinal variable is something that is ranked. Technically, no, but it's still done. I did it with my doctorate. There was no pushback from the statisticians on that, but you're making some assumptions there when you do that. So rule of thumb, best not to, but I think it might be allowed in some cases. It's debatable. It's debatable on that. So before we get into our final slide, let's do a little bit here on a section I call data reduction. Now, here's a set of scores here, and these are the ages of these individuals in my sample. On the low end, we've got an age of 6 years old. On the high end here, we've got an age of 28. Now, I can calculate my measures of central tendency, and I've done that here for you here. And this is an important piece of information. It gives me my mean, my median, and mode. And again, the values here, at least between the mean and the median, are pretty close together. But I still have all these numbers here, right? Is there a way that I can condense those values into something else to kind of give me a 5,000-foot view of what's happening here? And we can. And we call this data reduction. And more specifically, we call this putting things into what we call class intervals. And that's what we cover in Chapter 4. And what I mean by data reduction and class intervals is, what we mean is I begin to set up a range of years, right, that we have up here, a continuous variable, and I give it a specific value, right? And I might even qualify this as children, right? So children are going to be defined as between the ages of 0 and 12, and I'm going to assign that value a 1. So I know that in my reconfigured data set, anytime I see a 1, I know that that's going to be someone who falls in this particular range of years. I may not know their exact age range, but I will know the age range that they fall into. Thereafter, I might say 13 to 18 years old. That might be an adolescent, for example, might give a value of 2. And then young adults might fall into the range of 19 to 29 years, and I give that value of 3. And so this can be helpful. We've taken an awful lot of data. And imagine if this had been a data set of 15,000 numbers. Right? You want to do a frequency analysis on that. You kind of want to get a sense of, well, even though I've got my measures of central tendency, can I data reduce this a little bit to at least get a sense of where these folks are in terms of their ages? That gives us a second piece of information. And that's what data reduction can do. I've gone from a continuous variable and I've transformed it into an ordinal variable. And so let's summarize our key points for Chapter 2 together. Now, the first one is this. Dealing with every single data point or every single individual measure is simply not possible. So what do we use to help us make sense of the numbers? We use one, or you can use more than two, a measure of central tendency to kind of take an average. What is the average score, average value of a set of scores? And that score is supposed to represent the entire data set or the entire sample. Now, we know it's not, and we're going to get into that in Chapter 3. Okay, we're coming up to that. The mean, the mode, and the median are the methods or estimates that we use to measure central tendency. Outliers, we have to be aware of them. They can affect the mean, but not the median. And so in cases where we've got distinctive outliers, we want to use the mean as the measure of central tendency and not, we want to use the median, as the measure of central tendency and not the mean. 4 different types of variables or measures, each with varying levels of precision. That's where you get the varying aspect from. Continuous measures are the most precise, followed by ordinal, and then finally nominal measures. The type of variable used or the type of measure used will determine the type of statistic that can be used. And that's kind of important. That comes up a little bit later on. I'm going to come back to that last one. You can make mistakes along the way depending upon the type of measure that I use and the statistic that I want to use to analyze something or to analyze that group of scores. You have to line those things up. And this is where sometimes we get a little bit confused. Happens to the best of us. Trust me, it happens to the best of us.